So thank you very much for the nice introduction. That was the first time I was referred as a Dr. Popov. And yeah, thank you. And I would like to present to you today some of our currently ongoing research that is devoted to some new and interesting liquid crystal applications where the chirality is playing the central role. And I will start discussing our work related to liquid crystal sensors, because developing of a biosensor was our initial goal. So in this schematics on the left, you see this green liquid crystal film, nematic liquid crystal film, that is put in contact with an aqueous solution that may contain various biologically relevant surface active molecules. And when those molecules bind to the interface, they would disrupt the alignment of the liquid crystal, and that can be observed using the microscope. And this general idea was proposed by Professor Nicholas Abbott, and this approach became very popular in various laboratories around the world. And we have introduced some changes and added some improvements to the basic experimental setup. For example, typically this liquid crystal films, as you can see, there's a grid that has a bunch of empty cells in them, and the liquid crystal films are formed inside of those cells in those grids. And typically those films were supported by solid substrates. But we do these experiments in a little bit a simpler way. We just use freely suspended liquid crystal films. Then we also found that it's beneficial to also use circular polarizers together with linear polarizers. So we have a pair of circular polarizers here that distinguish left and right circularly polarized light. And then we also used a spectrophotometer to analyze the resulting light that propagates through the system, through the sample. And by combining all of these improvements and additions, now we can use a single liquid crystal film. We don't have to use a lot of those cells from the grid to average over all of those cells to analyze the final optical signal. Now we can just use one liquid crystal film. So imagine you have a single liquid crystal cell that contains a freely suspended nematic liquid crystal film. And these green dashes represent the orientations of liquid crystal molecules that makes this liquid crystal film. And it so conveniently happens that water aligns these molecules, the liquid crystal molecules, in a direction that is parallel to these interfaces. So water here is shown in blue. Now, when we add surface active molecules in the water, they will bind to these interfaces and they will change the alignment. And that can be observed using the polarizing microscope. And as the concentration of this surface active molecule will rise, these colors that we observe will change. And eventually, when the liquid crystal and water interface becomes saturated by this surface active molecules, we would see that the image becomes dark because of the complete reorientation of liquid crystal molecules from planar to vertical alignment or homeotropic alignment. Now, what happens if we replace this with biologically relevant molecules such as this phospholipid molecule? So again, we have a liquid crystal film that is put in contact with an aqueous solution, and this time it's made of phospholipid molecules. And before these phospholipid molecules start binding to the interface, we would see under the microscope that the films are more or less uniformly colored, or at least the colors vary very slowly, which means that these films, liquid crystal films, more or less uniform in thickness. And then when these phospholipids start binding, we will see that these dark spots start appearing and they grow in time. And those regions indicate where the liquid crystal molecules locally become vertically reoriented. And so we can already see a difference of detecting phospholipids from regular soap-like surfactants, because as you can see, the colors don't change in here. It's just that these dark regions appear and grow in time. Also, these phospholipid molecules, they have another difference from those regular surfactants that I have just shown. They are also chiral. And one question we have, can we use these liquid crystals to determine the chirality of these phospholipid molecules? And when I say determine the chirality, this is what we would actually like to distinguish. So imagine that we have these phospholipids of different chirality. So one of them is these enantiomers have different handedness. And we would like to use liquid crystal films to be able to distinguish between those. They look very similar, but they're not the same. And it made sense to us that if we want to sense the chirality, we should use a chiral nematic film, or so-called cholesteric film. And to make a cholesteric liquid crystal, we use this well-known 5-CB compound, and then we added a small amount of chiral dopant to it. And what that does is, when we have such a cholesteric liquid crystal, we'll have these 5-CB molecules that will spatially rotate. And so now let's look at what we see under the microscope when we form a cholesteric liquid crystal film in air. So a freely suspended cholesteric liquid crystal film in air will be flat, and under the circular polarizers will exhibit a fingerprint texture. And I also used a green filter just to enhance the contrast. But then when we immerse this film under the water, this this fingerprint texture relaxes, and a new texture appears. As you can see, this nice set of rings appear. And we figured out that these rings appear because the film becomes curved. So it makes kind of a convex lens, convex microlens. And when we analyzed the curvature profile using the intensity map, we found that the surface is nearly spherical. So as you can see, the blue, maybe it's not very easy to see, but this blue curve represents the real microlens surface profile that we've determined from the intensity map. And the dashed red curve represents the ideal spherical section, or like a section on a circle with that particular radius. And typically, production of such good lenses requires very involved and complicated fabrication processes. But in our case, these microlenses just self-assemble by themselves. So according to our current understanding, this happens because these liquid crystal film, when it's submerged underwater, is trying to minimize its free energy. And the way it does that is it's trying to become thin at the edges to minimize the distortions that arise near the edges of that grid that holds the liquid crystal film. This is a work in progress, and this is our current understanding, but that's what we think happens right now. And so, as I said, these forms microlenses, and if it's a microlens or it's a lens, then it should be able to do something like this. It should be able to take parallel beams and put them together in one point. And when we look through such lenses at distant objects, we should see something like this. So imagine you have a magnifying glass, which is also a convex lens, and you look at some distant object. And like in this example, you look at a house behind, and you'll see that the image that the lens is forming will appear in front of the lens, and it will be inverted. Okay, and but we produce this really tiny microlenses, and we cannot really directly look at large objects like that. So we should find something small to look at and also use the microscope for these purposes. So we are going to look at this small number 50 in honor of the 50th anniversary of the Liquid Crystal Institute. So this number 50 is one of the markings on a microscope calibration slide that you see on this picture on the left. So 50 is somewhere there. It's hard to see. And so here it is. You see this 50. And when the microscope objective, so imagine the microscope objective is somewhere here. And when it's close enough, we can see the actual object, that number 50 that you saw in the beginning. But then if I lower down this objective a little bit, I can focus on the lens itself, which just happened. And then if I lower down the objective some more, then I can focus on the image of that object that the microlens is producing. And the focal length of this microlens can be easily determined by measuring this object distance and the image distance. And we can also obtain the focal distance from the from the curvature profile from this intensity map. We can calculate this R1 and R2, which are the radii of the curvature. And then we know all of the refractive indices, and we know the thickness, and we also get this focal distance. And we see that both methods are in very good agreement. And so far, I showed a single cholesteric lens, but we can even see an array of inverted images if we use an array of such cholesteric microlenses. So here I just focus back at the microlenses right now. And now I insert the circular polarizers to see the texture, to see these rings. And I also insert the green filter just to enhance the contrast, or for clarity. Maybe not the contrast really here, but for clarity. So the consequence of chirality of the liquid crystal phase is self-assembled cholesteric microlenses that are formed underwater. And in nature, similar, but of course more complex arrays of lenses are used by various insects. And of course, these insects don't really see repeating images of whatever they're looking at. Their eyes are more complicated, and they only accept normally incident light. But that's a different story. And so that was a surprising, these microlenses for us, that was a surprising and interesting effect. But now I would like to return back to the liquid crystal sensing of chiral molecules. So again, cholesteric films underwater typically looks like this. They haven't relaxed yet, so these rings are not looking very good, but this is what they look like typically. And after the addition of phospholipids in the water, the following typically happens. So this fingerprint texture appears. And these fingerprint textures, they are like signatures of different surface active materials. And we also have a question, like, is it possible to use these fingerprint textures to be able to distinguish between different chiral enantiomers of a particular phospholipid? So here we compare the resulting responses of the cholesteric liquid crystals to the absorbed phospholipids of different chirality. And from the first glance, it looks like these fingerprint textures are quite very similar. But if you become very picky, then you can see that the periodicities are different depending on what's the handedness of the phospholipid, of those phospholipids that got absorbed to these cholesteric films. And possibly we can also analyze the morphology of the texture and check if we get closed loops or spirals and so on. And of course, in different experiments, the textures are never the same, but the general patterns should repeat as long as the conditions are kept same. So this kind of analysis can be similar to the forensics investigations of fingerprints left by criminals. And fingerprints from different people, they look very similar, but the forensic investigator can clearly identify who left those fingerprints. So our fingerprints are even similar to the fingerprints of other primates and even some marsupials. And perhaps a forensic-like image analysis can be of great help to us. And to conclude, we have shown that chiral pneumatics definitely produce self-assembled micro lenses underwater. And we have some indications on how cholesteric liquid crystal sensors might distinguish chirality. And as I said, this work is in progress, and we are open to interesting suggestions. And thank you very much, and I'll be now happy to take questions.
I enjoyed your talk, Piotr.
Thank you.
The question about the fingerprint analysis brings up the question how you would process that image. And what I thought that the rotatory motion in that image can be analyzed by using Fourier transform or some other processing of that type. Have you by any chance applied to the images that you obtained in order to distinguish one enantiomer from the other enantiomer?
As you can see, if I go back, maybe this slide, for Fourier analysis, you would want this map to be much larger so that you can average over many of these lines. If I use an area just this big, the Fourier transforms are possible, but they're very noisy. So to do this, we would need to average over much larger films. But yeah, it is possible.
But can you, in one cell, in the other cell, in the third cell, so not just on one lens, but over a few of them?
Mm-hmm. Okay, so you're saying that we should actually not look at single cell, but again average over a lot of cells. Yeah,
I think so. I think that would
yeah, we can do this. But when we were using just the pneumatic films, then I was saying that you don't need that much liquid crystal, and we can just use one cell. And but in this case, we'll have to use many to average over, to have more information for the Fourier transform. And of course, it would be much easier to see the differences if you do a Fourier transform, because you will see you will see the differences on the Fourier transform faster than in the real space. There will be some dots or maybe some structure that can be easily right away identified. But yeah, that's a good suggestion.
Any other questions?
Just to be straight, you did not see this lensing in pneumatics, only in cholesteric?
Only cholesteric. Does not happen with just pneumatics. No.
And how are you controlling thickness or the amount of material that you put on these cells?
Oh, okay. Well, this is the hard part. This is where the art happens rather than the science. It's a little difficult to make very uniform films, or it's very difficult to deposit just enough liquid crystal so you have exactly 20 micron thickness. And sometimes you can even do it in such a way so that you smear the liquid crystal in a way that you know that I have more liquid crystal on this part of the grid than that. And I can see that the ones that are very thin, they have fewer rings. So that means that they have smaller curvature. And the ones that are thicker, they have more of those rings. So they have higher curvature. But of course, it depends also on the thickness, depending on how many rings you'll have. But that part is hard. And I don't know if Oliver is here, but so a lab mate suggested a good way. I haven't tested this yet. But so the idea is that you do this in cold water. So because for example, pneumatic like 5 CB liquid crystal will become crystalline below something like 20 degrees Celsius. So if you put it in contact on one side, you just touch it. You don't submerge it yet. You just touch the water. It still stays flat. And that will allow the film to crystallize. And then when you submerge, the thicknesses will not change. Because this is another problem. When you submerge, the water kind of snaps and changes the thicknesses. Yeah, but that may help.
One last question.
On this slide there, can you describe the interaction between chiral liquid crystal molecules and these molecules that you add?
Mm-hmm.
Can you describe what types of interactions they are having?
That will be hard to do, but so the liquid crystal is already chiral. But, and as you can see, and I think the chiral dopant that we have is right-handed. And when we have a right-handed phospholipid attaching to the surface of the liquid crystal, it kind of helps it become even more right-handed. So we see that the periodicity is smaller. The pitch of the observed pitch becomes smaller. And when the phospholipid is of the opposite chirality to the chirality of the liquid crystal phase, it kind of tries to unwind the liquid crystal. It helps doing that. And then we see that the periodicities here are larger. Another thing that I can show you is,
How do you know it's not just that the planes are coming out towards you and they look further apart?
a lot of these things I don't understand yet. As I said, this is like a recent research, and so we will be happy if someone also gives us clues, but I'm not really sure how exactly that happens. But here, for example, what I know, I'm not talking right now about chirality, but so here you have a cholesteric liquid crystal in contact with a particular surface active molecule, which is again in this case a phospholipid, but it can be just a regular one-tailed surface active molecule like a soap surfactant, and it will produce these change in textures towards this fingerprint texture. And we know that our pitch of the cholesteric liquid crystal, when it's under planar alignment, it has an intrinsic pitch to be maybe like 5 micron. But when we do these fingerprint textures, while having this vertical alignment, we see a different periodicities. And when we use different surfactants, those periodicities are changing. And that has to do that there is the observed pitch when we have a fingerprint texture. So it depends on the intrinsic pitch when we have a planar alignment, but then it scales with some coefficient here that I don't really know the form yet, but it depends on the anchoring strength, and also it depends on the elastic properties of the cholesteric liquid crystal, and it depends on the thickness of the film. That's how much I know now. How chirality, I don't have anything that depends on the chirality here to be so that, because I would assume that the physical properties of both enantiomers of those DLPC phospholipids are probably the same. And I would assume that if I use both of them, then I'll get the same observed pitch. But it's not true. I'm seeing that one enantiomer is having a different pitch. So there has to be something else in here that depends on chirality that I don't know yet how to include it, how to incorporate it. But that's a good question, yeah.
Let's thank Dr. Popov again.
Yeah.